l'UCLM. Ensuite, Irastorza Valera, également rapporteur de l'UCLM. Mohamed Jebali de l'INSAM. Et Luis Ousseino Mopa du PM. Donc, on vous donne la parole pour 45 minutes. En anglais.
Thanks for everyone for being here today. I will continue in English so everyone can understand. I will take questions in French. I'm Irastorza Valera. I'm here to present my doctoral thesis work entitled Learning Techniques for Division in Engineering, Data-Driven Tools for Mechanical and Biomedical Settings, directed by Professor Sinesta from ENSA and Irastorza from UPM. We have divided the work into three thematic sections. The first two of them regard structural problems. First, the design description. From geometry we get some generalized properties or some behavior. And the inverse problem, design optimization. From a target property we obtain the structure yielding the characteristics. We have profited from the goals developed for structural optimization and design to develop a mock-up of a biological system in accounts of the similarities between nodes and graphs and biological networks. And we have mimicked the signal transmission throughout the brain. The first block consists on discrete geometry. It can be periodic, parameterized or not, composed of a unit parameterized cell and some other conditions. And with those initial data, we apply our solver. It could be generate our ground truth data. It can be usual finite element models, finite element methods, or fast-fourier transforms to accelerate dynamic responses. And we predict the result with machine learning surveys. That is a way to bypass the costly methods by machine learning. We obtain finally some mechanical properties that can be static or dynamic behavior as a response. The inverse problem, design optimization, starts with a target property or a target behavior, another set of boundary conditions, and the solver is now an optimizer. Usually topology optimization, that is a methodology to generate topologies, geometric architectures for a set of boundary conditions, for example in SIM, solid isotropic material generalization. We get an initial design space and we apply some static boundary conditions and we reduce compliance with a limited volume. We add our own extra criteria to alleviate SIM shortcomings that we'll see later. And this can also be illustrated by machine learning surveys. As a final result, we obtain a geometry that can be discrete, composed of beams or struts, or continuous, like the designs on the right. Lastly, the biomedical section takes advantage of all these codes developed for structural applications to mimic that signal transmission throughout the brain. You can see an example on the right, how these synapses in green activate the second step in propagation in red. We start with simulated data coming from mathematical processing of in vivo data coming from electrophysiology or hemodynamics. And joining together artificial and biological neural network concepts, regression, activation, backpropagation, and migration or neuroplasticity for the biological consistent model. And we end up devising digital twin, a sort of cheap, fast mockup to mimic this nerve transmission. That can be used, for example, for diagnosis of illnesses if nothing does not go right. We can see how it affects signal transmission. Unfortunately, due to time constraints, we will be focusing mainly on the structural part and we'll leave this for discussion. As an outline, after a short introduction, establishing the objectives and the general context for the problem, we will set Some results will be given for case studies related to our objectives, and some discussion, are they accurate, are they generalizable, are they fast, are they cheap, and some conclusions generally will be drawn from all this work. Starting with the structural problem. This project is part of a wide European, this is part of a wide European project called Meta, dealing with 3D printed metamaterials. Metamaterials are microstructures whose geometry, whose topology is designed, is conceived to create some unseen material properties in the bulk material at the macro level. For example, offsetting metamaterials, where a zero or negative Poisson coefficient, and left-handed materials can yield a negative refraction index, which you find in regular materials. According to their applications, there can be 4 types: electromagnetic, acoustic, thermal, and mechanical. We will focus on mechanical. And they feature a parameterized unit cell with a given set of lengths and geometric characteristics. These amount to a Taylor property, and usually, since these materials are composed of many individual unit cells at the micro scale, they have a lot of degrees of freedom that become usually intractable to traditional methods. For that, we need standardized ways to get a material description from its geometry and vice versa, to get from a target property design that is feasible, that can be manufactured, and has real industrial applications. For that, we develop chip surrogates to accelerate the procedure. Coming to the structural description, there is the direct problem linking given parameterized predefined geometry and its properties. We have some examples, like the access to metamaterial uses this kind of reentrant cells for negative Poisson coefficient. This is repeating among all directions in space. Since this is too costly usually to tackle by finite elements, there are some techniques that can alleviate this problem, that can make it faster. For example, assuming a continuum back behavior through homogenization, taking representative volumes or areas with homogenized properties to represent the full material. Or we can develop machine learning surrogates, feed as an input images with topologies, geometrical parameters, etc., to get through several neural network techniques to get the mechanical response or the mechanical property we want to predict. In a setting where we have all the data we need to construct our model or to measure it for observability, we can just build a very large database, in this case composed of parameterized unit cells with the same boundary conditions, vertical displacement and restricted degrees of freedom on all other directions. And for generalization capabilities, we can assume there's an unknown number of inner nodes apart from the vertices, which are loaded. And we can assume this cubic unit cell can be sliced in all 3 directions as we slice a spring in series system in 1D, and we know the equivalent statements can be computed by just knowing the amount of equally stiff members, equally stiff springs. Now our objective is to predict a homogenized property that is just modulus in the Z direction or any other direction for that matter. And for that we train 2 neural networks. The first of them is a tensor network composed of linear array layers that treats data as vectors and matrices. And we train a more sophisticated architecture called GNN, graph networks, which has a built-in topological advantage. It has an edge embedding through message passing techniques. This information concerning the physical evolution of the system, in this case stiffness, can be transmitted through nodes, through the struts, to the nodes. And in the nodes, there's another embedding built in, which takes the information coming from the edges and updates the value upon the nodes, and then it keeps going until they reach equilibrium. This way, we can learn the geometrical characteristics of the lattice, at the same time the physical behavior and the conservation laws for the nodes. some results. We can see our hypothesis is verified. We can just predict with almost exact accuracy the stiffness of a one discrete string system, no matter how big it is. So with that hypothesis confirmed, we can do the same for 3D. How to decide the number of slices that will be optimal to describe the system? Well, if we select too few, we get a T model, but not accurate enough, not complex enough to represent all variability in our data set, which is quite big, about 100,000 samples. However, if you choose a 2D parameter, 99 slices, for example, we'll end up with a complexity that is not feasible, it's not convenient for this kind of application, so we settle for the middle ground. And between 19 slices and 49 slices, we see the difference in prediction is not great, so we prefer the cheapest option, 19 slices. With 19 slices in all 5 directions, we get the results on the right for the pin-jointed truss, that is the assumption in which we only have axial strength along the struts. This is the simplest case, and the density network predicts quite accurately with good adjustment coefficients and low losses. However, the complexity of a richer mechanical framework, for example beams or frames, is not enough to be tackled by GNNs. For that, we recur to GNNs because of their topological features. And first of all, we can see the prediction for pin-jointed truss is slightly better, well, quite better in fact, half of the loss and an almost exact adjustment coefficient. And we can actually deal with the beam problem. With the most complex, we can deal with all these extra degrees of freedom, extra restriction, momenta, etc., with similarly good results. In partial observability settings, that is, we don't have access, or we are not aware of all the variables needed to build an analytical model. There are only some conditions in which we can build a model linking observable inputs to observable outputs. Usually, in mechanical applications, we can condensate through Gaussian reduction these unobservable or internal variables that we cannot measure or we are not aware of into the observable degrees of freedom, so we can sort of bypass this problem. However, this model will only be useful as long as these internal conditions don't vary. So, for generalization capabilities, instead we train a surrogate based on a recurrent neural network, giving the output and the input and the previous output. In this case, our system is comprised of Kelvin-weight elements with a spring and upper and parallel and some oscillating masses. And we want to learn the evolution of the last one with ignoring without the information from the inner part. How can we do that? We set position as an output and force as an input, and we feed it to the recurrent neural network. X is going to be F, and H, the hidden internal state, is going to be the previous output, the history. It's a way to keep the sequential evolution. If this is not enough, we can use more sophisticated structures like LSTM, low short-term memory, with different gates to forget, include, or potentiate this information to a hidden cell state, conveying the record of history keeping for previous states, not only the preceding one. Here are some results. In a case where we have 3 elements with their own frequency oscillating forces, transform can give us a hint on how many forces are present. However, it doesn't give any information on the evolution, especially if we introduce nonlinear aspects like the dependency of stiffness on the previous displacement, like we did here. For 3 elements, RNN and LSTM perform well. However, there's a big difference. LSTM is almost 10 times more precise because of longer training and longer history keeping, because the memory needed is quite large. However, these are testable results with under 1.5% relative error. Regarding a more complex system, we introduce explicitly monotonically increasing time variables like this one, and we reduce the symptom two elements. We obtain similarly good results, although a bit worse for RNN and LSTM. However, we can still perform the task. Again, LSTM is more performing than RNN in the same process. And remarkably, LSTM can even deal with highly nonlinear responses, like for example, path dependency. We make stiffness depend not only on the previous displacement, but also on the previous stiffness itself. It becomes highly nonlinear with these kind of responses. And LSTM is still capable in that evolution within errors under 3%, which is a thing to note. For the inverse problem, as we were saying at the beginning, the most usual procedure is topology optimization. In our case, we use SIM, solid isotropic material optimization. So we start with a given set of boundary conditions, static, in modulus and position, given loading. And we start with an intermediate density field material, which is eventually penalized as the P for a given volume fraction, that is a percentage of field material in the dominion, to get the least compliant option, that is the safest. It has some limitations, however. For example, this static assumption does not consider service loads, vibrations, displacements, mismeasurements, which are very common in industry. This isotropic assumption is also damaging, especially considering we want theorem isotropy rather in metamaterials or functionally uniform materials. And also, perhaps, the starting point is not the most convenient one. We could either develop a topology from an existing one. We will deal with those problems later, to give our own solutions, but some alternatives that are commonly used in industry are either generative metamaterial design, to come up with a lot of possible, in this case, discrete-based, strut-based lattices that will serve as individual cells in a periodic metamaterial, and then we can sit them, we can filter them through our own criteria, if they are stiff enough, if they buckle or not, for example, how much volume is filled. We can also use the model reduction to simplify the features describing a network or an individual metamaterial cell, to simplify the design until we reach convergence for the simplest option. And we can also be inspired radiology in the separation of cells through membranes, following one-way diagrams or Delaunay triangulations, which are dual graphs, and deciding the boundaries with the help of deep learning. This will yield a continuum-like behavior, as the directions for individual cells they are aperiodic, yield mostly homogeneous properties. For discrete media, a quick result would be to search within the already generated database. We have a lot of options, existing topologies with a given assigned label and computed stiffness, and modulus. So an easy way is to search within that database, selecting a second option, a second design criteria. In this case, inverse volume, so the end weight, which is a common engineering design criteria. And we can draw the Pareto from, that is the maximizing value for each of these variables of existing, the boundary of existing topologies within that database. So for each stiffness or weight range, we get the optimal solutions that we know exist. We have characteristics already computed. Regarding static configurations in topology optimization, we wanted to address this because we consider it unrealistic and rather limited. So we drew inspiration from Brodler's curve and Millet's law, establishing a damage, accumulated damage in fatty engineering, proportional to the contribution of each load in frequency and in modulus. For that, we introduce a gamma parameter that is going to penalize as a damage-like function sinks to main variables, that is volume and compliance. This is going to be done for a full iteration. Each load is going to have its own probability associated from the distribution. They can no longer be static, they can be applied all the time, that means a frequency of 100, but they can also be drawn from statistical distributions, normal distribution, for example, student, etc., or alternating forces. And each of these loads, if they come from a distribution, they're going to have their own cycles amounting to that penalization. So in the end, at 3 levels, cycle, load, and loop, we penalize and we give each load their own weight instead of oversizing it as is common practice for load envelope approaches. Here we have some examples for a cantilever beam fixed on its left side and loaded on the bottom and top corners on the right side. For the 50 and 50 loading case, that is same modulus in the original case and same frequency in the modified case, we see very close designs, very close topologies. The only difference might be the axial struts at the very end, fixing, uniting load the application points. However, this modified approach becomes important and relevant when loading is skewed. When loading is not symmetric, the traditional approach tends to ignore a lesser load. So it ends up forgetting about the 20% share load on the top or on the bottom. That is, however, taken into account with the modified approach, since it's proportionally weighted instead of major to 1. Also, volume is much more leveraged more heavily in the modified case, since we don't really need these pins on the left side. So instead, we use that volume to reinforce junctions and delegate points that will lead to fatigue or fracture. Another example of this modulus and frequency equivalence is the loading case on the bottom. We can see for a deterministic case, loading 1 Newton and 9 the other is equivalent to loading with 9 and 1 respectively. In the probabilistic case with the same frequency, and that is also equivalent to loading with the same load at weighted frequencies, so 10% and 90%. And even we can play with the load value as long as the product for modulus and frequencies is kept constant. For example, we can apply 100 load for 1% cases and a unit load for the rest of the time, and they still have the same configuration, which proves the equivalence, and that proves how this is equivalent to Miller's rule for fatigue. Let's see an example now with distributed loads. We have this cantilever beam loaded on its top right corner and middle bottom, with horizontal loads, which are well taken by traditional approaches, but also with distributions of load in modulus and position, which are not quite well taken. We'll see why with the traditional results, the deterministic case, since the horizontal load has a univocal and constant and static contribution, it does affect the gradient. However, for each iteration, it's taking a random sample for this distribution of loads, both in the top and the bottom, and this distorts the gradient direction. It cannot converge to a definite topology, since all the time they are assuming the static load applied all the time is a sample from the distribution rather than the distribution itself. So our solution is to weight this contribution through their probabilistic value and damage given by the user and probabilistic value given by the distribution itself. And if we penalize this way, the gradient is quite well computed for each iteration, because for all the cycles, each representative sample from this distribution is going to have their own weight. They are not oversized as in the load envelope approach. So we get quite more intuitive and reinforced designs, like the ones on the bottom, for several damage configurations. However, they do share a reinforced contour linking loading points and a quite wiser distribution of inner stratum transfer load. It's all for 0.4. These pockets that we saw in the previous slide may be interpreted as a lack of convergence. However, if we interpret them as intermediate densities, or in a practical case, in a printed piece, as intermediate thicknesses, we can actually take advantage of this fact. We can actually burst because this intermediate thickness is still stiffer. The intermediate density is stiffer than void, so we can interpret it as a sort of inner interface between void and material as a thickness value above the bottom. To deal with this isotropy assumption in SIM, we have introduced two custom tools. First of them is the already mentioned damage function. We can penalize material to make it accumulate along directions that we want, precisely because of fatting restraints, like in the first criterion. We are penalizing areas which are prone to fatigue development, to develop cracks, or to propagate them. We can also penalize the printing direction, as is common in composites. The stiffest direction, the most performing direction, is the fiber one. So, in an analogy, in 3D printing, of course, the stiffest direction is the one along the layers. So, we would prefer that most material reallocates along the layers instead of however it wants in an isotropic assumption. We can also penalize a given stress state, so a given stress response, traction or compression. We want to prefer traction for steel or cables or to avoid buckling in general. Or we would prefer the opposite, perhaps compression or working with concrete. Also, as a last damage criterion, we can introduce von Mises current stress itself as a measure for the limit for plastic deformation and distortion in general. The second tool is a density filter. Density filtering is quite common in industry technology optimization. However, it's usually done as a post-processing step, which is costly and it's inefficient because all the changes we want to include in the topology are already too late to be dealt with. For example, it's very common that in this kind of topologies, we see a lot of intermediate, very thin struts that are not actually, in theory, they are contributing in fact to the optimal design. However, not significantly, and this volume, instead of adding this fragility and this extra compliance coming from the formation of all these tiny struts, we would prefer to reallocate this volume along junctions and along socially meaningful parts to get simpler options, simpler topologies that are easier to print. For that, we devise a very simple density filter, searching for lower density neighboring areas for itself with a given radius, and interestingly, with a Taylor search direction, so we can introduce Taylor isotropy like smearing material, which is common practice in other filters, like in the right image. For the additional criteria, this is an example for three-point bending. We can see how the fatigue criterion actually reinforces areas prone to fatigue. Joints and junctions are thicker, and the areas prone to stress concentration are reinforced with auxiliary struts. For the printing criterion, when the printing is horizontal with zero angles, triangle, layers are horizontal, so most material is reorganized along these horizontal lines, avoiding purely vertical struts. The opposite is true for the vertical printing criterion. We avoid horizontal struts for the most part, unless they are inevitable. As you can see, for example, the horizontal strut is completely forgotten in exchange for a more complex topology, still able to carry along to the supports. In the compression criteria, we get most of the material working under compression. The thickest struts are working under this state, and we minimize the contribution of non-compressive areas. And the opposite is true for traction. At the cost, again, of a much more complex topology, we get a layout in which most of the struts, at least the thickest one, are working in traction as we want it. That will be useful for metal or any material with similar characteristics. We have this criterion with a minimal deformation option to control this distortion energy. You can see the some similarities between the compression criteria and the horizontal angle criteria and the vertical one and traction. That means they are synergy. We can combine them to create similar effects. And we know which combinations to avoid. For example, zero traction will have opposite effects. In this period, we're going to evaluate the mechanical response. On the right, on the left, you can see the equivalency of this stress. And on the right, you can see shear strength. In the fatigue penalized approach, the fatigue penalized topology, we can see clear stress concentration at the loading point as expected, but also middle joints, which is dangerous for fracture concerns, although lower than in the original case, and in the bottom horizontal strut, and similarly for strain. To alleviate that, we can come up with criteria with unload this horizontal strut, for example, the lower printing angle, which in turn for increasing slightly the concentration of stress in the loading application point, it unloads the horizontal strut. If we want to unload the thinner junctions in the middle, the thinner struts within the contour, which are the most prone to fatigue, which are the most vulnerable, we can combine some synergy criteria like higher printing angle, 60 degrees, or traction penalization with foam mixers to reduce this deformation area. At the cost of maintaining loading concentration in the loading point and slightly increasing it for the horizontal stand, we have successfully unloaded the inner joints that were our main issue with the first model. As for filtering, we can see an example for 1,000 iterations here. We can see a clear difference first in the volume itself. It can become quite simpler, let's say cleaner, without all these inner thin strata that we're not actually contributing significantly. And adding a lot of compliance, a lot of deformation energy, which is taken off, reducing compliance, increasing stiffness in the filter case. Also reducing volume, because we don't need all this extra volume used by these thin struts. And the mechanical response is also quite different. While gradients here in the unfiltered case are quite steep, with very high local concentration points for stress and strain, which are complicated to deal with and are another a red sign for fatigue and fracture. Instead, in the filter approach, we get a much smoother distribution with in which the concentrations are along struts, along the same strut, which are easier to deal with. We can just make it thicker or substitute that particular strut, which is quite simpler than actually reinforcing a lot of very tiny focal points, like in the unfiltered case. For strain, we have practically eliminated any strain concentrations, and the gradient is clearly much smoother. Another example of filter applications is, apart from the stress reduction, is tailor anisotropy. We can tailor the direction in which struts are appearing, so the direction in which stress concentration will appear. For example, consider the unfiltered case in the middle for a cantilever beam, again loaded on its left side. You can see the evolution on the bottom right, as here. If you see the concentration areas for high formation stress over 0.5 megapascals in gray, you can see how they take part of most of the structure in the unfiltered case. However, if we progressively apply filtering with ever-growing radiuses, we get tinier and tinier pockets of stress, and also lower displacements in the vertical application loading point. If you do that for only diagonal or orthogonal vertical directions, you can do that for partial areas, thus creating tailor anisotropy. Then, as a suggestion for the improvement of this topology optimization scheme, we have drawn inspiration from actually small linking relative densities and relative stiffness, and Carter Hayes' mechanostat theory of bone remodeling, linking density growth to strain energy to a growth parameter E. If we combine that, we can derive this equation linking compliance and volume, which seems two main objectives. The compliance is minimized and volume is a restriction. And this allows for the creation of these curves stating the topological family, topological evolutions within the same process. And since we have control over volume and compliance separately, instead of restricting one again C, this is very interesting for biomedical applications. We need a stiffness field for prosthesis, or for acoustic or vibration applications. We need to tailor very accurately the coefficient between stiffness and mass, which is equivalent to density in this case. Let's see some examples. Consider the evolution of a molecular process starting with volume 0.3, the green curve. We get the evolution on the right, on the left, from C to B to A. These are stages of the same, virtually the same topology with the same genus, same number of holes. However, as they approach the stiffest possible solution, which is the full block, these strips thicken until they occlude naturally some of the holes, and eventually they become the full block, as we see in the GIF in the bottom left. Different families, different topological families starting with different volumes, have their own pros and cons. With lower volumes, we get much more restricted designs, which takes a lot to evolve into the full block. For example, take D as an example, and we start with like F, with high initial volume fraction. The design space is so restricted that we cannot do much, apart from filling up the entire block. What's interesting is that B, E, and F topologies, so this one in the middle, this one in the middle right, and the one in the bottom right, they have virtually the same compliance. They are equally stiff. However, they are very different in layout and in volume fraction. This will depend on, as a criterion for an engineer to decide on which design to consider according to material cost or material behavior. Also, interestingly, since this is different to SIMP, in SIMP, point E and point A, so this one upper left and this one middle right, would be an evolution of one will be an evolution of the other. Since SIMP restricts the volume in a vertical line and lows compliance, and this is the inverse of compliance or stiffness. In this case, A would be an evolution of E, which is clearly not the case since they have very different features. This proves the difference from our method to the common approach. Interestingly, we can combine these properties from different topology curves. We can travel from one point to another, for example, from point B to point A on the bottom right, from point B to point C, and merge these features as density fields. In the end, they are all compliance and volume matrices. We can sort of hybridize them and get features from each of the curves, depending on how much time they spend the process in one of the curves before linking onto the other. And this interpolation can be done horizontally, fixing a compliance limit, like in these cases, or vertically, like in SIMP. If we add the filtering radius as another parameter, that would be equivalent to the minimum thickness for struts, we get a wide design space with three main variables: compliance, volume, and minimum thickness. As we said before, the options for lower volumes do not vary a lot because the design is too close to void, too restricted to have any meaningful impact or radius that doesn't perform any real changes in the topology, and that's the same case for the higher volumes, for higher volume fractions, in which we are very close to the full material, so the design space is much more restricted. However, for middle values, 0.3, 0.4, 0.5, we will get an opportunity, a window for tailoring designs with virtually the same compliance and volume points, which row-wise, they have basically the same compliance and volume. However, the layout is quite different, especially for the 0.5 case. As a way to accelerate this optimization process, we can also start with a different initial condition. Instead of the SIMP start, which consists of an intermediate volume matrix with 0.5 density, which it doesn't belong to any of the SIMP curves. We could rather start within a curve already computed with known topologies. Consider, for example, the one linking topologies A to E. You can see evolution for A, C, And if we want to know, to get a design close to a design point, a given strain density energy, strain energy density, which is equal to compliance, is 2 times compliance or density, which is equal to volume. If we want to approach, for example, say point P3, instead of traversing all the corresponding curve, or the pin curve until the end, that would take many iterations. We would rather get a closer design starting from nearby points C and D, which are close in compliance on volume. To do that, we train a neural network composed of linear array layers, so similar to our dense initial configuration for other studies, with points in non-topological curves that we have explored. We have the data, we have their compliance volume density maps. And with this image, we can read those density maps and train the network to get compliance and volume values close to our target. With losses concerning the distance between the non-curve or non-topologies, and concerning the distance between the non-curve and the curve in which our target and non-target is, and we have not explored, we know nothing of. With this compliance and volume data, we can reintroduce this value into the topological optimization process to obtain an existing topology close to our target without having to compute the corresponding curve. We can do that to further accelerate the process for database generation. For example, for points A to E in our non-curve, we get very close designs for, in this example, for C and D, especially when the filtering radius is low, because the designs are sharper, and since the network reads for the images, it's easier to interpret the volume and density map. And not so much, but still quite acceptable for higher radius, since these intermediate density areas are difficult to interpret. But still, it's a way to boost the database generation part. To get this design point that we were discussing, the initial curve, points P1, P2, P3, and P4, we have trained for 500 epochs the neural network and obtained the designs on the top row. And on the side, we have iterated for 2,000 times the iterative process until getting the ground truth corresponding to that state. And you can see there are some similarities between the top and bottom row, especially in points closer to the non-topological curves, that's point P1 and P2. Perhaps not so much for P3 and P4, but still quite close. And interestingly, we can extend this accuracy by, instead of starting with the initial block, with the initial known curves, for training the neural network, we could rather stay with a more advanced stage, with the 5th iteration of our process. Just 5 iterations are enough to bridge the gap between these responses, and you get virtually equal designs in the middle row. Interestingly, this is also the only way to predict a full block evolution, since to predict a full block, as you have trained with only non-full topologies, the only meaningful way to add this within the network is to feed it a full block as a starting point, as in this case, so we can correct this block. Some general conclusions, we can say that neural surrogates can provide seed and accurate simulations in areas where analytical solutions are too costly or absolutely impossible to implement. There are different machine learning techniques and data structures for dealing with, architecture for dealing with different data structures. Consider, for example, graphing networks for graphs, consider convolutional neural networks for images, MLPs for vectors, etc., RNN-LSTM for sequential data. These methods, these surrogates, these bypassing techniques can yield high fidelity property predictions, even in the absence of clear topological definition and nonlinear behaviors. And these topological definition schemes can also be reinterpreted, reinforced to disrupt this static or homogeneous and initially isotropic configuration to get a more rich, like a richer topological space. And finally, these graph-based data representations can be leveraged to apply structural methods or structural printing and testing of prototypes in PLA and metal, like the ones I'm gonna show you right now. You can examine in PLA, carbon fiber, and resin. We will continue to print this also in metal. And we are already working on extending this criteria to 3D and surface level definition methods. We are going to do two-scale material optimization of the prototype from the cell level. Reduced order models should be used to accelerate fast responses for material evolution, behavior evolution, and our response. We have data to create a hyperelastic brain damage model to introduce injuries and how they affect signal transmission throughout the brain. And this will result in the creation of free use software suites that everyone can enjoy. As scientific contribution, we can cite 4 peer-reviewed papers. 3 of them are pending regarding the optimization findings. We published the results, we presented results in 5 international conferences, and 1 public talk as an outreach talk was given, certified by ANECA. Here are some references for the images used in the presentation. And I will thank you for your attention, and I'm ready for any questions you may ask. Thank you.